Okay, today we will complete our discussions on testing of motors. This is very important and critical from industrial point of view, as how after a motor is manufactured, you need to know how they are tested. And since single phase motors are manufactured in millions, they are perhaps the machines which are produced in the largest number in the world today, single phase induction motors, right. See, every house has 10 motors, single phase motors, is not it, minimum. You find air conditioner, refrigerators, fans, table fans, blowers, compressors, okay, exhaust fans, you find them all over of different types, etc. But when they are produced, and nowadays they are also produced mass produced, it is not the human beings which are producing single phase motors. Who are producing? It is robots which are producing them today. Windings are done by the robots, okay, all the things, it is all numerically controlled, okay, and the stampings are done like that, you should see an industry where it is done. Now, when they are done like that, when the robots can make the machines, robots should also test the machines, right. So, that is the speciality of these small machines. So, if you make a large generator, you take 6 months to make one generator. So, you do not mind taking another 15 days to do the testing, right. Whereas, if the time taken for this itself is small, you make maybe 100 motors a day. So, you should have a mechanism to test it, right. Now, we will specifically we will see the testing of single phase motors today, and these are some of the instruments which we have discussed in the last lecture. And nowadays most of the instruments are getting digital, and we would like to have some sensors, if you automated testing, but accuracy is important and traceability is important, okay. And what are the quantities you want to measure? Typically you want to measure voltage, you want to measure current, you want to measure power, you want to measure temperature, you want to measure speed, you want to measure torque. These are the things you want to measure, okay. So, these are typical instruments which are in our laboratories, which are fairly sophisticated instruments, and maybe as one group which is doing a project on testing of induction motors, I want them also to list the instruments that we have, okay, in the lab, and see how accurate they are in the testing of motor, right. So, these are the the non-contact type of instruments which are used for measurements, okay. And today that energy audit has become an important factor. Energy audit, how much energy that is consumed. I had told you to measure how much power that is consumed in each of the gadgets. When your electricity bill goes up every month, you should know why it is going up and which is the energy guzzlers, okay. And the motors are one of the major ones, right. Okay, so this is a power analyzers where you connect it and it measures the voltage, current, power, and you can measure the harmonics, etc. Okay. So, if you come to specific the single phase motor, why you do the testing? We have already seen we do testing because we want to find the equivalent circuit parameters. We have an equivalent circuit, I want to know the parameters, okay. Then we would like to know losses in these motors, right. What is the difference, and efficiency has becoming important. Recently we concluded, our department, a project was taken for the LG Korea for improving the efficiency of their motors in air conditioners, etc. So, they wanted the efficiency to go up from 90 to 92%, okay, even that was important, right. So, it was a critical issue to see how to minimize the losses in this, okay. Then what is the performance under load? How does it perform when you load the machine, okay, from no load to full load, how will it perform, okay. This is one is you perform. Now, one other test in all the machines, one test you do or one family of tests you do is you make sure that the output is 0. We call it as a zero output test, right. In a motor you have 0 output tests, is it clear, okay. And other family of tests is you put a load on the motor. So, this is output is 0, another the output is not 0. So, here is P out is 0, here is P out is not 0. Okay. How do you get the output of a motor 0? I want the output of a, what is the output of a motor? Any motor, what is the output? Power. What is the output power? Say P output is the torque output into speed, is not it? Speed in, of course, if you want in watts, torque will be in Newton meters and speed in radians per second. Okay. So, torque and speed. Now, what is 0 output? How do you get 0 output? So, one is torque is 0 or speed is 0, is not it? Two tests you can do. How do you make torque as 0 on a motor? Output torque as 0. How do you make the output torque 0? No load, do not load. See, when you say you are carrying 0 load on your head, means do not put anything on your head. That is all. That is 0 load. So, no torque means you do not load, free running, right. So, that is one thing. And how do you make speed 0? Block the rotor, right. These are the two things, and sometimes you broadly, sometimes you call it an open circuit test and short circuit test, right. So, one way to do is, one test is torque 0, other test speed 0. Is it clear? Okay. So, now let us look at these tests, what will it mean? So, first thing you want to measure the parameters. First thing you do is the resistance. You have main winding, auxiliary winding, you want to know the resistance. Okay. So, you can measure, you apply a small DC and measure DC current and measure the voltage across it and say this is the DC resistance, is R is equal to V by I. Simple. Okay. Or you can put a bridge method. Are you aware of bridge method of measurement resistance? Have you heard anywhere? Where you in physics you heard? You have heard of Wheatstone bridge, Kelvin bridge methods by balancing this. Okay. This is a very accurate method of measurement. So, the bridge method of measurement and the electronic method. Okay. So, this is ohm meters, micro ohm meters are there. Okay. So, it directly gives you either analog or digital signals, digital displays giving you the resistance. So, you can test it. In fact, I had told one group to do testing of single phase motors, right. Now, this is one you must do and check whether they all give the same reading. Okay. Now, you do the testing at what temperature? At room temperature, at lab temperature, which is normally say cold temperature, is not it? When you do the testing for resistance, you do it is cold, right. You do not heat it up and then do it. It gets heated up when it is in operation. Okay. But actual operation, if you want to see, it is a hot resistance, right. Now, how do you, if you have measured the cold resistance, okay, and I think it is you want to measure the hot resistance. Okay. Now, this is the formula, I think it is TH and TC. Have you heard of this formula? RH is equal to 235 plus TH in degree centigrade divided by 235 TC in degree centigrade into RC. How does it come? You know that resistance varies with temperature, is not it? Okay. And that variation is in what temperature, in what scale? Kelvin. I hope you heard of the Kelvin. Kelvin is 235 plus degree centigrade. So, RH, RC are the hot and cold resistances. Huh? What is 235?
235 comes from the temperature coefficient of resistivity for copper.
Yeah. Okay. So, it is like this. Okay. Now, if you plot for example, because you involve the resistivity of copper also into the calculations. Okay. And so, this is one of the, so if you want to know the resistance hot versus temperature hot, okay. So, it will have a, from that what does it say? It seems to have a linear relation. So, you can, let us say, some linear relation, okay. This may be degree centigrade, this is in ohms. Okay. Now, this is one thing. So, you have measured as say 25 degree centigrade, it has this cold temperature, let us say. Okay. So, it is 235 plus, so it will be 235 plus T hot divided by 235 plus T cold into resistance cold temperature, that will be resistance hot, okay, hot resistance, right. Now, it is this concept, okay. If you go to negative temperatures, what happens? You can reduce the temperature also, not that it will increase the temperature, right. What will happen? Supposing I go back, what happens? Huh? So, this is the condition of superconductivity, where R is 0. You can pump thousands of amperes with no resistance, so no power. But this is one other thing, they are using large generators, large transformers, levitation, magnetic levitation and things like that. So, this is a technology which of course people have been experimenting for the last 30 years or so, but somehow it has found very limited use because of the problem of cryogenics. Okay. Now with this you know how to find the resistance, you have found the resistance, simple test. Okay. Now, I do blocked rotor test, so where speed is 0. So, what is slip? Is 1, is not it? Speed is 0, slip is 1. So, you have an equivalent circuit. What was the equivalent circuit we had? You know, single phase equivalent circuit we had was this is what you had, no? This was the equivalent circuit you had. I hope this you do not forget. Okay. Right. This is one thing you should be knowing. Now, what will you do with this? Put S equal to 1 and what is the equation you get? Okay. What do you get? Put S equal to 1. So, you will have RS JXLS JXLR okay. So, it is same as a 3-phase motor also, single, is not it, no change. So, you have impedance Z will be Z short circuit or blocked rotor will be RS plus RR plus J times XLS plus XLR. Why? Because you consider magnetizing reactance very much more compared to This branch you neglect, you make it as open circuit, you can, because that magnitude is very large compared to the parallel branch. Okay. So, from the parameters from block rotor test you can easily find out, okay, and that is you have the R block rotor will be RS plus RR and X block rotor will be XLS plus XLR, is not it? You know the impedance, you measure the impedance under block rotor test, okay, that is what you will have, and you know RS by the stator resistance measurement. So, RR will be RS you may know it, because resistance RR will be equal to R block rotor minus R stator, and you normally you can assume, see XLS XLR division depends upon the parameter. Now, one approximation is you take XLS equal to XLR equal to X block rotor by 2. This is one simplification do. Depending on the type of machines, there is variation of 60-40, 70-30, 65-35. No, that's usually done by the design. Okay. Okay, this is one thing that you will do. Okay. Now, if you do it at rated voltage, you have one reading, but if you vary the voltage, you may have different reading also, because there is some saturation of the leakage paths. Okay. So, you may observe that if you plot X blocked rotor versus the I blocked rotor, it might have some variation like this, there will be some saturation. Okay. So, it may be the what are the, so it may depend upon reading, may depend on I, on temperature, on frequency. Supposing you conduct block rotors different frequencies, their readings may be different. Why? You do block rotor tester on that machine, say from 10 hertz to 50 hertz. I would say your readings are likely to be different. Can you tell me why? What could be the main reason why the readings may be different if you operate different frequency? I do it at 10 hertz, 20 hertz, 30 hertz, 40 hertz, 50 hertz, 60 hertz. So, yeah, that is true, that is one thing, but so what? See, the reason is that you have assumed XM is very much greater than RR, no? That is what you have assumed at frequency. But supposing this may be true at 50 hertz, but it may not be true at 10 hertz. It may be comparable also, right. Therefore, the readings may change. Incidentally, I suggest that you read the book by C.G. Winnett. Here just a couple of pages. He has said, he says how to find parameters accounting for XM without neglecting XM. Is it okay? And it is a little, involved derivation maybe, but not too involved, but I thought because of limitation time I thought I will skip it, but I would suggest that you read this, it is just a couple of pages is there. Okay. It is given in the original book on fractional horsepower motors. Okay. So, as I told you, this will be temperature, input current and frequency, the readings, right. Now, you repeat for auxiliary winding also. Okay. So, auxiliary winding what you will have? You have V auxiliary, R auxiliary, XL auxiliary and this will be what? XLR refer to auxiliary turns and RR refer to auxiliary turns. Now, is not it the reading that you get, these will not be the same if you do it both the tests, and this will be a separate, the resistor leakage reactance will be corresponding to the auxiliary winding, okay, as you do for the main winding. It will be, therefore, this will be a little involved process. So, in fact, you can try to find out turns ratio A, which you decided n auxiliary by n main, no. Auxiliary to main winding, there is a turns ratio. Now, obviously, from this XLR, when they are referred to auxiliary winding, this will be, you do the measurement and try to see whether you can find a turns ratio in this way, because you do not know the turns ratio. In a simple transformer you can find out approximately, but here it is different. Okay. Now, this test is done. Now, another test I call it as no load test or synchronous speed test, where you find torque is 0, is not it? Okay. Now, what will be the equivalent circuit there? Okay. Now, I will do one thing. One is it is a little involved. You can conduct a synchronous speed test, that means run it at synchronous speed exactly. So, n equal to ns and find the input impedance. Will it be same as no load test of 3 phase induction motor? Why? Because here there is a backward field also is coming to the picture. Suppose S equal to 0, what will be the equivalent circuit that you draw? And you go S equal to 0, you draw the equivalent circuit. Okay. This is say V naught, I naught, RS, JXLS. Of course, this will be corresponding to the main winding. Okay. Then what you will have JXLR by 2. Will it be there or S equal to 0? Is it relevant? And then what will happen to the rotor resistance? S equal to 0 means RR by S is infinity. So, you do not bother about it, is not it? So, you say this is useless. Okay. Then what will you do? This will be J XM by 2, and this is, that means this will be what we call it as VG forward, is not it, across this. This is the total voltage which is induced in the winding will be due to the forward field and backward field, and the voltage due to forward field we say is due to this ZF. Then what will happen to the other one? Let us look at the backward field. Backward field is it also open? It is not open. This will be RR by what? 2. Okay. So, RR by 4, yes, RR by 4, right. And what about this? There will be XLR by 2. Okay. What will be XM? Can I neglect it now? XM by 2. So, I will neglect this. So, this is open. This branch is open, and here this branch is open. Okay. So, you have a have understood, if you run the machine externally by a synchronous speed and measure the input impedance, this is what you will find. Okay. And this will be the current, magnetizing current, which will be flowing. Okay. So, you will have a mechanism of finding the Z naught will be what? RS plus RR by 4 plus J times XLS plus XLR by 2 plus J times Xm by 2, is not it? Of course, if you neglect core, if you include core loss also, then it becomes little more involved. Okay. So, you can find out Xm, right, because you know RS, RR, maybe XLS, XLR like that. Okay. Now, this experiment, if you do no load test also, you will get some readings. Okay. So, you can find the parameters here. Now, what is concerned in this test is level of air gap flux is important. If you conduct the test at different input voltages, okay, from 0 to rated value, air gap flux will be different, is not it? So, air gap flux different levels of magnetic flux and magnetic saturation, right. The core gets saturated differently at different flux levels, okay, and there will be different forward and backward fields. Now, in synchronous speed, what we have found is there is effectively no backward field. See, this one compared to this, if you see, this is the current I naught, VGF, what this is VGB. You find VGB is very small compared to VGF, is not it? So, bulk of the voltage goes to forward field at synchronous speed. Why? We always said this current in the stator winding produces stator MMF, okay, stator gets magnetized, so, and the flux is decided by how much rotor is magnetized, is it? I am hammering up again the same point. Now, this due to forward field there is no current in the rotor, due to forward field there is no current in the rotor, therefore, rotor is not magnetized at all. So, all the flux is due to this. So, the bulk of the flux flows because rotor is dead, no current in the rotor bars due to this thing, whereas due to the backward field, backward stator MMF will have terrible opposition from the rotor because all the current is flowing here, whatever the I naught is flowing here. So, it is total opposition, it is like a transformer where the secondary is short circuited, it opposes all possible way primary MMF, is not it. So, here all the stator MMF is totally opposed by the rotor MMF, therefore, there is absolutely no flux under open circuit conditions or synchronous speed conditions. So, this is you will observe is a phenomena which is different than 3-phase induction machine. Okay? Any doubt on this? I mean, we should, every time I write theory, you must also have some explanation, physical explanation. Any doubt on this? So, under synchronous speed conditions, bulk of the flux is forward, no flux backward, although there is a equal forward and backward MMF due to the stator winding. Okay. So, we will now say forward backward fields are important. So, if you plot say Vg versus Im, I mean Vg forward versus Im, you know that current which is flowing through Xm by 2, if you consider this is Vgf. So, you expect it to have some type of saturation curve, is not it? This will be interesting, you can do this test in fact, okay. In fact, I thought if somebody can develop on LabVIEW, it will be a very interesting experiment, okay, these tests, right. Okay, so, this is one way where no load test will be slightly different. No load test, in actual no load test is really not no load because there is enough of input power is going, it may be no load from the definition, but it will not be running at synchronous speed. So, even on no load for a single phase motor, there will be considerable currents in the rotors because slip is even on no load there is a considerable slip. So, slip should be made 0 only by synchronous speed test. Okay. Now, there is one method which is proposed by VNet called turns ratio test. If you do not know test, from if you know bit design, if you know turns ratio, there is no problem. Okay. So, what you do is you test it at same speed and same flux on both windings with other open, right. So, what you do is say first you do is main winding excited, auxiliary open, right. So, what do you get? You get some voltage VA, is it open circuit voltage, right. So, that means in this case what you do is IA is 0, IA is 0, but you have applied a, therefore, Vm, but Im is not 0. You are exciting the main winding and keeping the, you are running, that means it is running at some speed, there is N is there. It is, you are just running the machine, this test is run the machine with main winding with certain voltage, okay, and auxiliary winding is open. So, this Vm will be equal to, you know that ZL M Im plus EFM plus EBM, is not it. Now, the voltage induced in the auxiliary winding, I call it as EA dash, will be JA times EFM minus EBM. You have done this with double revolving field theory. What is the auxiliary voltage? With JA times EFM minus EBM. Okay. Now, similarly, if A excited and M open. So, what you do, but you want to have the same speed. So, flux is also approximately same. In fact, he says you apply around certain percentage more than this. So, apply EA, therefore, what do you have here? That means you have VA, sorry, with ZLAIA plus its forward EFA plus EBA. Okay. And then it induces a voltage EM dash which is minus J by A EFA minus EBA. Okay. Take this read. This is the, that means what you do is you take these readings Vm EA dash, okay, and VA EM dash. Okay. Here one side is IA is 0, another side is IM is 0. So, you take these two readings and these two readings. Okay. And you know these equations. So, you can find out what will be, you will see that EA dash by Vm will be, I have done the derivation, you can just check it up, A into half Im into ZF minus ZB divided by ZLM Im plus half Im into ZF plus ZB. This is the ratio of the induced auxiliary voltage to impressed main voltage, induced auxiliary voltage to impressed main voltage. This is in terms of the Im, you know. Okay. Then you can do the other way around, that VA by EM dash, that is ratio of the impressed auxiliary voltage to induced main voltage, second test. So, you have a relation A times IA into ZLA plus half A square into ZF plus ZB divided by half A square IA into ZF minus ZB. Okay. You get these two relations. I mean, you can verify this, it is just a matter of simple algebra you have to do. Okay. Now, you can, from this you can prove that EA dash by Vm into VA by Em dash, okay. You can prove that this is equal to A square, okay, right. You can just prove that, okay. So, if that is the thing, you have a relation that A is equal to square root of EA dash by Vm into VA by Em dash. Maybe I will write it again, square root of okay. This will be the equation for A. So, you can find out the turns ratio by this test, because you do not know it from the design. Okay. Now, another thing you have to know is you have done the testing and you want to separate the losses. Okay, what are the losses in a single phase motor? What losses will be there? What are the losses? There is the core loss in the core, okay, copper loss in the copper, okay, and friction windage where there is friction. So, these are broadly the thing, okay. So, copper loss in copper, core loss in core, and friction windage, where is the friction windage loss? Where there is the friction? You do not have friction windage loss inside the core or a copper loss in the core, right. So, core loss is in core only, and now core loss is not in copper, okay. So, iron loss is in iron and copper loss is in copper, just like you can't have headache in the stomach, no. You can have headache in the head only, right. So, these losses are identified where they belong, okay. Now, so the stator, you have the stator copper loss, rotor copper loss, the core loss, friction windage loss, okay, isn't it. So, how do you separate them? See, whatever at 0 output tests, whatever power that you goes in, what it goes for losses. In a block rotor test, well, there will be some input power, where will it go? Block rotor test, for what losses? Mostly copper losses and very limited core loss, because you operated low flux. In a open test, you, since the current is small, it invariably goes for core losses and friction windage losses, okay, and smaller in copper losses, okay. Therefore, one method of finding this, okay, again these have been explained in the literature considerably. In fact, I prepared some write up, I can give you for this today's lecture. I myself have prepared the write up, okay, so that you can go through it, okay. Now, okay, so you just plot the losses versus the voltage, okay. You conduct the test at different voltages, okay. Now, if the curve is like this is the power input, okay. In this power input, there will be certain stator copper loss. You plot power versus voltage, okay. Plot power and current also versus voltage, okay. Then you will also have maybe rotor copper loss, okay. Subtract stator and rotor copper loss, you know the rates, okay. Then there will also be maybe another curve, the rotor copper loss, okay, not the other curve, sorry. I think then this is because there is one loss which is not supposed to vary with voltage. What is that? Friction windage. That will be almost very if you draw a horizontal line. So, I suggest that when you conduct the test in the lab, you try to separate out these losses. So, you can, and that will depend upon the operating voltage. So, you conduct a no load test or induction motor at different voltages, measure the power and try to estimate this, and this is a method of separation of losses. I think for details I still say you refer to this book. Okay. Is explained in a couple of pages, okay. Now, you want to do a direct load test, this is another test that you would like to do, okay. So, I think you lab or something like that, okay. So, any motor is there, so you connect a pulley, isn't it, this is load that you do, isn't it, this is the motor and you have a loading system. So, I think there are several ways. Okay, and you say this is T1 and R, you say the torque is equal to T2 minus T1 into R, isn't it? See, one is a slack side, another tight side, you see. When you rotate it, one part this, so one if you do not rotate it, both springs will be at the same way. Okay, this is pulley and weight arrangement. Sometimes you do not put anything, and there is a, you can also think of you put a weight here, okay, this and this you do not put anything, okay. So, this is the R and this is the torques, I mean are the force or something, torque will be F into R. Okay. So, this is a small machines, you have to improvise, have a small aluminum disc and put some strings and put a accurate spring balances and do this. This is purely a mechanical way of doing things. Of course, there are also, okay, sorry. Of course, there is also, you can have prony brake. That means you put a brake, supposing this is the one, you put some type of brake and and then some pressure here and this, okay. So, this is also a method to know this. There are some of the mechanical ways of testing the small motors. So, the latest ones is using dynamometers. Test it electronically, and this is one of the systems which we have in our lab, okay. And then this is by a company called Magtrol motor testing equipment. Okay. Now, you can do several type of small motors, it will tell you whatever motor to be tested, etc. Of course, if I have a their manual here, this is the motor testing, this company motor testing equipment is a computerized motor testing facility. Okay. So, yeah, okay. Now, what is the type of, then it will tell you maximum torque, speed, power of the motor, and then it will, you can also test the parameters, and how do you plan to control the, that means the dynamometer is a hysteresis dynamometer, and you can collect the motor test data. Okay. And it can vary, it has several models, it can vary as low as 0.110 Newton meters to 56 Newton meters. It has hysteresis brake, through hysteresis, because what is a brake? Brake is create loss, okay. There is hysteresis brake, you can vary from no load to locked rotor, okay, and you can have accuracy of all models full scale. Okay. This is the actual system. You have a inline torque meter, you can measure the torque here, okay. Then there is a gearbox, then there is a hysteresis brake set, because this is coupled to the motor, and then there is a speed encoder here, it measures the speed, okay. This is the dynamometer, hysteresis brake dynamometer, and this has a compressed air source, because you have to, when the heating is done, you have to cool it also, right. So, you have to compress the air, so there is enclosures, etc. Okay. So, then it can test different type of motors, it has hysteresis brakes, gearbox, no backlash, the torque meter is there inline, and there is a speed encoder. So, torque and speed everything can be monitored. Okay. So, this is the system, you have a motor under test, this is the dynamometer, and there is a dynamometer controller, and there is a GPIB interface, it is connected to a computer. In fact, incidentally we have this system in our lab. I have asked one group to conduct these tests, right. So, you please do this, then there is a GPIB interface, and it can control, there is a thermal relays, power supplies, and power analyzer is also there. So, it will automatically measure the readings of the machine under different operating conditions. Okay. So, it has customized, it has enclosed dynamometers, programmable dynamometer, power analyzer, softwares, power supply, computer and printer, GPIB cards and cables, and there are couplings. So, these are all supplied by the consumer. So, the system will typically looks like there is a motor here, okay, and there is the coupling here, and this is the dynamometer, this is the dynamometer, okay, and there is the power supply, etc., and power analyzers. Okay. So, you have lot of your work is done by the company, and for which you pay anyway, right, it is not free, right. Then I mean, this is a closed loop system where you can put how much torque you want, all this, the settings are possible in this closed loop system. So, there is the thermocouples are there is a dynamometers. So, you can get the signal from this, and then through the computer you can operate different possible testing. Okay. So, it has this offers, there is a motor, M testing means motor testing, T testing means temperature testing. So, you can do the measurement of temperature as well as the parameters of the machine. So, both programs are window executable files and written in LabVIEW. Okay. So, this is, I mean, more details are available in this manual of this book, and I am sure before you use any of this, you read the manuals, okay, and you can do all these tests, ramp test, torque curve, speed curve, torque stabilize, constant torque, constant speed, constant current, constant power, and you can do some manual tests. That way you can set these numbers putting on the computer, etc. Okay. And under defined tests, you can have 1000 users, they claim, these are the claim of the company, any user, that means user can define the test he wants, and maybe it will be customized. Okay. And the temperature test, you have a data acquisition analysis of up to 7 thermocouples, that means it can measure bearing temperatures, winding temperature, housing temperatures, etc. So, because these are the requirement of industry, because even noise is also important, because small motors, if it is operated in your office, it should not make noise. So, all these things they have to measure before it is sent to the customers. Okay. So, I am, since these are the state of art, I thought I should tell you Okay. So, we have told, I have covered the testing methodology for last 50-60 years, originally from old type of meters up to the latest one which have uses sensors, computer interfaces and data acquisition systems, and you can do a lot of testing on this. So, it will be, I think it will be interesting for you to go through this and conduct the test, because they are still very important from practical point of view. Okay, we will close it here and we will start, all discussions induction motors are over. So, next we will take other than induction motors in next class. Okay.